Hello, we are presenting on an image forgery detection survey paper. I'm Joel Quarnstrom.
And I am Ross Thompson.
So the paper that we read looked at a variety of different image forgery methods and detection methods, and we'll be presenting about 6 of them. They are cloning, resampling, splicing, JPEG compression, 2D and 3D light detection. And so here we go. The first one is the image feature cloning. So with cloning, whenever you have a forged image, usually the image is made up of multiple images spliced together, or you take an image and you take part of that image and kind of duplicate it, either to duplicate some feature in the image or to cover up a feature using some blank part of the image. And this can be very visually hard to detect, as you see in some of these images. But they are able to detect these issues with kind of a clever system. The first method is the discrete cosine transform, and this is very similar to the Fourier transform we all know and love, but this one is a real valued function as opposed to a complex valued function, and it just uses the cosines. So what it does is it decomposes an image into these frequency basis functions, these 2D basis functions that are shown in this image. And then you have a list of coefficients for each basis function. So you can find patterns in these coefficients if there's duplicated features in an image. Another way that they can detect this is the principal component analysis. So with PCA, the image is broken into small blocks, and these are sorted. And so if the blocks are sorted to be close to each other, that means they have same characteristics, and that can identify duplicate blocks. And that will show that there's 2 different places in the image that have the exact same pixel structure. And that would be forgery. Another thing that happens whenever you splice images together is usually part of the image is resampled from either scaling it or rotating it. And we've all had experience with this, being able to see artifacts in rescaled or rotated images. So if you have a given signal and you resample it with a larger sampling ratio, you can find, like if it's by a factor of 2, you'll find that every other point in the new signal will be the average of its neighbors, and that's a good indication that there might have been this interpolation process going on. So with detection, researchers have been able to come up with a metric that measures the likelihood that a given pixel is copied from one of its neighbors using some interpolation method. And so if there's a periodic pattern of these, the likelihood that certain pixels are copies of its neighbor, then that is a good indication that that portion of the image was resampled and tampered with. And so you can see that this shows up in this frequency domain image down at the bottom of these images of this forged image on the left. So another type of something that goes on is when 2 images are spliced together, there's a border between the 2 images, and one of the ways to detect a forged image is looking for this border. And so the border introduces a certain nonlinearity to an image, and you can measure certain signals using what's called a power spectrum, and something similar to this is what's called bicoherence. And the bicoherence has both a magnitude and a phase, and these will show certain characteristics whenever excessive nonlinearity appears in a signal. So if you take an image and you compute this bicoherence across different windows in the image, you'll be able to see how nonlinear that section is. And so for this image that is shown on the left, on the left half of each of those signals is the original image. On the right half is a spliced signal. And so the discontinuity there in the center, whenever the window of the bicoherence is over that that spliced area, the phase plot kind of peaks and the magnitude plot changes in pattern. So you'd be able to detect these splicing using this method, which is pretty clever.
Right, in the next section of the paper, they looked at specifically features of the JPEG compression format itself. So JPEG is the most common image compression format. In fact, most of the cameras that we have, including cell phones, directly output images in the JPEG format. And an important property of the JPEG compression format in terms of detecting possible forgeries is that it actually shifts the distribution of pixel values during the compression process. So when you take an uncompressed image and compress it, the distribution of pixel values changes. And also, when you do a second round of compression, even if the image is unchanged, the distribution of those pixel values can change again. So to back up and give you a little background on how the JPEG compression algorithm works, at the high level, the algorithm first converts from the RGB color space into this new color space that we haven't talked about in class, which is called YCRCB. So this is somewhat similar to the hue saturation and value in the sense that we have a Y channel, which is like the value channel, but then this CR and CB channels are color difference channels. And the main idea here is that the JPEG compression wants to make use of the fact that our human eyes are less sensitive to color information than they are light intensity. So the color channels are downsampled while the luminance channel Y is not. So then JPEG takes each one of these color channels independently and then partitions them into what are called macro blocks of 8 by 8 pixels, and then performs that same discrete cosine transform, the DTC, to convert them into a real valued frequency domain representation. So up to this whole point, the entire JPEG process has been a completely lossless and reversible process. This next step, quantization, is where the actual compression comes from, and where, in fact, the techniques for image forgery detection can come into play. So each one of the pixels, or the frequency domain pixels, will be divided by some quantization factor called A. And so this factor A actually controls the compression ratio. And so as A increases, our compression ratio increases. So in a JPEG image, you take the 8 by 8 grid of frequency pixels as DTC coefficients, and they get divided down by this coefficient table called the quantization table, and that produces all of these now reduced value quantized DTC coefficients. And this produces two important results. The first is that the division is not a floating point. Instead, it is an integer. And so it rounds down to the nearest integer. And second, when you round down to 0, right, you end up producing a tremendous number of 0 values. So this is where the actual compression comes from. So the fact that you have these two lossy components here rounding down to the nearest integer and down to 0, that's what makes both the compression and the change in the distribution values of the pixel values in the histogram. So what happens when we do double compression? So the idea here is we can actually tell if an image is saved once by the camera and then once again by somebody who has either attempted to modify the image or done something else to the image. So the reason we can detect this is that the quantization is not reversible, right? So the inverse dequantization is not the exact opposite function because of that rounding down property. So what happens is the quantization involves these two flooring operations, and this introduces a change in the distribution of the pixel values. So this top row of distributions show the result of the histogram after a single round of JPEG compression. But the second row shows a distribution of the same image, but having been saved twice. So no other manipulations have been done to the image. It's just been saved twice. And what's really interesting is you can see that some of the pixel values have been shifted from one bin into another. And in this first example, like you actually have a significant transformation where some of the pixel values are just completely lost. They've been completely moved to another one. And then in this other image, some portion of them have migrated to a different band. So we decided it would be really fun to actually see if we could reproduce this result ourselves. So I took an image with my cell phone and I set it to produce an image saved in the highest quality JPEG setting as possible. And what I did is in MATLAB, I had it produce a histogram of specifically the Y channel. So this is not the RGB histogram, it's just the Y channel, so that the luminous channel. And on the left-hand side is the histogram of the original JPEG image, and then on the right is the histogram of the JPEG image after having been saved a second time in GIMP. So no other modifications to the image have occurred. So the histograms look fairly similar, but if we zoom in really this one section, you can see that there's a pretty smooth transition along this section here. But we can actually see that there's a slight perturbation in the values. So some of the pixel values have shifted from these bins over to their neighbors. And so this is actually a real effect that is actually something we demonstrated in an example. Okay, so moving on, another forgery detection technique is to try and estimate the direction of light in an image. So imagine you have a scenario where you have two actors or celebrities who are, scandalously potentially romantically involved, and someone has come up with a great idea of splicing two images of them together. Well, we could potentially try and figure out if this image is a forgery or not. And the idea here is we can look and see how the light strikes the different objects in the image. And the core idea is that we can actually take the normal to the surface of that object, and we can estimate the direction of that light using something called a Lambertian. And assuming that the light is infinitely far away, we can actually estimate the direction of that light. And so in this image here on the left or on the right, it's really obvious, right, that the light is shining in from the right side. And then this equation down below here is actually a way we can go about computing and saying, okay, yes, the light is coming in from the right side. A more advanced way of doing this is through 3D light modeling or 3D light detection. So this is more than just saying, is it coming from one side or the other, but actually trying to figure out a more precise direction of the light. And this is done through a model of the human eye and actually trying to figure out how the light reflects off of the eye. So the idea here is you set up three vectors, L, N, and R. L is a vector pointing towards the light source away from the eye. R is the light reflecting from the eye into the camera, and then N is the light, or is a vector that is perpendicular to the surface that's normal to the eye. And the law of reflection of light tells us that the angles between L and formed between L and N and R have to be equal. And so we can use this equation down below to actually estimate the direction and magnitude of L. And then if you have a bunch of eyes in an image, as you might have, we can infer a much higher quality estimate of the direction of that light source.
And if any of the eyes are looking away from, or the direction of the light in the eyes is looking away from all the other eyes, then we know that that's probably been tampered with.
All right, so in summary, as our technology develops, right, forged images are going to become harder to detect. The advancement of artificial intelligence is going to make this become much harder. But the good news is that image forgery detection is also going to improve along that same line. These fields are going to be something that are going to be entangled together for a long period of time. It's going to be an arms race. And that concludes our presentation.
Thank you.